Alright, so first of all, you're very welcome to the School of Engineering here at Athlone Institute of Technology. My name is Ronan Dunbar. I'm a mechanical engineering lecturer here in the school, and I'm going to be running through a lecture for about 45 minutes now on the special topic. So question 1B on your Leaving Cert engineering paper this year is all on basic principles of operation and applications of the rapid prototyping processes. So we're very lucky here. I suppose our mechanical engineering department back in the day, back in the 70s, was built upon our ability to run these courses in polymer engineering more so. We were renowned for polymer engineering courses. And it kind of slacked off a bit because the manufacturing industry shifted to, eastern countries where all plastic manufacturing was done. But now it's starting to lift again here in the Midlands because of high-end polymer processing. So medical industries, etc. There's a hell of a lot of them in the Midlands, and now it's taken up again. Our research in the area of polymer processing is taking off again because those companies need us to carry out research for them. So we're very lucky that we are able to carry out most of the rapid prototyping processes here on campus. We'll show you some examples of some of them today, but more so I'm going to talk about exactly what it says here, the basic principles of operation and applications of the rapid prototyping processes. I won't get to pass around examples to you here in the lecture theatre because it's not an ideal environment for it, but later on you'll also do a workshop in rapid prototyping where we'll actually get to split you up into smaller groups, talk about it in a little bit more detail, let you look at actual, some of these examples here that I have here in front of me, etc., and then talk in a little bit more detail about how rapid prototyping is used in the different industries. Okay, so let's get started. So I suppose before we actually start talking about the rapid prototyping process, it's important to consider okay, we have a group joining us now. Connor, how are you doing? All right, come ahead. So I suppose it's important, first of all, to talk about the design process before we talk about the rapid prototyping process. All right? So, every design process begins with a problem that actually needs solving. All right? So a company identifies a problem that they need to solve, and as a result they initiate a research phase. Okay, so their research and development team, or their R&D team, they sit down and they start to research solutions to this problem that they have. All right, and then eventually conceptual solutions. So you're all fulfilling your design brief, your design solutions for your Leaving Cert project at the minute, yeah, and you're asked to do a concept sketch 1, 2, and 3, and then come up with your final solution, which might amalgamate good ideas from your 3 design sketches, etc. All right, so it's quite similar in industry, where a research and development team will all sit down, come up with ideas, try amalgamate those ideas to come up with the best solution. When they think they've come up with the best solution, that's when they'll go to the prototype stage. Okay, and they'll start, now this image doesn't come out great here it's quite small here, but what this tried to depict is they're trying to design some sort of a backpack for a hiker, okay? So the concept sketches are done, and then maybe more detailed, maybe CAD modeling, even using Photoshop to get photorealistic images of the product, etc. But then they start to actually prototype the object, okay? So we can learn a hell of a lot from looking at a 3D image of an object. And it's great, to compare a 2D image of something to an actual 3D SolidWorks drawing. When you're able to manipulate and rotate a 3D SolidWorks drawing, you can learn a lot more from that CAD model. But even more so if we take a prototype of something, so you can imagine the prototype of this hurl, it's very advantageous to be actually able to hold a prototype. And this prototype, I don't know if you've heard of the company Hurlog, if you have younger brothers, sisters, or nieces and nephews. Hurlog are a company that started to manufacture kind of foam, soft hurls for younger people, younger kids, right? But they wanted to get them manufactured in Taiwan. And the Taiwanese had a distinct disadvantage that they didn't really have a clue what hurls were. Okay, so Hurlog said that they needed a prototype to be able to send out to the engineers in the manufacturing company out in Taiwan so that they could actually hold the object, all right, see what it was like, interact with it, see and these are very important terms, and these are terms that are going to get you marks on this question 1B. See what the fit, the form, and the ergonomics of the object were like. Okay, so to be able to actually hold it, okay, a CAD model is great, you can manipulate it and look at it, etc. To be able to hold it and actually figure out how the hand actually interacts with this handle, etc. Because if you looked at a CAD model of that, if you've never held a hurl, you might think, oh God, we could surely put finger imprints into this to make it a little bit more ergonomic, etc. But we all know, having held a hurl, that, that'd be overkill, right? It'd be over-designed, etc. All right, so So the prototyping stage it gives us the advantage to actually take the product, send it out to market, so send it out to possible consumers, possible customers for the product, and let them test and evaluate it for us. Okay, so we might think or the research and development team might think that, this is the best design, right? But they might have overlooked something that the consumer, the experienced hill walker in this case, might actually be able to point out for them, etc. Right? And that's the real advantage of the prototyping stage of the design process. All right, so before we go on to look at the rapid prototyping process, it's important to know where it sits within the design process. And then when we get that feedback, then we can either revisit the design, or if we're happy with it, it can be sent for manufacture. Okay? And I suppose in the manufacturing industry, it's never cheap to get an object manufactured. Okay, there's a hell of a lot of development that needs to take place in order to get an actual object manufactured. Whether it's develop new tooling, whether it's to develop, molds for an injection molding machine, whether it's to develop a workshop floor that will have a suitable flow so that the object can be manufactured, etc. And that all takes a hell of a lot of money. Okay, so it's critically important that before we send it to the manufacturer stage, that we're happy with the design, so that we don't invest all this money in an object that at the end of the day isn't going to be actually what we require. All right, so that's where prototyping, it's seen as low cost. All right, but to get a prototype developed by a company will probably cost them thousands. Yeah, but that's still seen as low cost because it cuts the risk out of developing a manufacturing process and then that manufacturing process not being correct. Okay. So to talk specifically about, so this is an interesting case study of the Lilly baler, okay? So this was a company where they had all the expertise within their company to develop and design all the internal workings of the agricultural machine, okay? But what they didn't have and what they were struggling with was developing a cover for this to actually make it look modern, to make it stand out in the marketplace. All right, now, unfortunately, I couldn't get an Irish case study of the McCabe baler, etc. But these decided then, the company decided that they were going to go and work with this innovation lab, Flex. All right, to actually develop just the cover for this baler. All right, they had all the other technology developed, designed, and were happy with it and how it worked. But it was how this actually looked is what they wanted to perfect. All right, so you can see here, the grey part of this image is all a CAD model. All right, so that's what the engineering team at the company were able to develop themselves. But this here, the red part, is actually a concept sketch. Okay, so it's sketched on over the actual design of the baler. All right, so this was the initial stage that the Flex innovation team started to work on with them. Okay, and in essence, that is a prototype. Okay, so a 2D sketch is a prototype. It's the initial stage usually, it's the initial prototype stage, and it's called a low fidelity prototype. So low fidelity means that, it was very easy to produce, there was very little investment in it, and it can very easily take comment and very quickly changed. All you do is produce another sketch or make slight changes to this concept sketch. So that's the initial stages. Then they went about still a low fidelity sketch, creating foam models. All right, and this is a prototyping step that I'm sure you've all been advised by your teachers to do in terms of designing your Leaving Cert projects. Go home, get the Kellogg's cornflakes box, cut it up, create your cardboard models. Because it's looking at a drawing is one thing, but actually having a 3D object will tell you a hell of a lot about how your final product is going to look, how it's going to feel, and how it actually fits together as well. All right, so you can see here they're starting to develop the cover here overlaying it on the existing baler, or the existing geometry of the baler. And then they went and produced, so that's a photorealistic 3D CAD model. So that would have been modeled in the software like you use in your school, something like SolidWorks. All right? So now you can imagine that, they're happy with the design. The company, Lilly, are coming back to the innovation lab saying, well, yes, definitely, that's how we want our baler to look. You've come up with a futuristic design that's going to make us stand out in the marketplace, etc. So now they're able to extract that part and actually start to produce scaled 3D, rapid prototyped 3D printed models of it. All right? So nice, interesting case study of the design process and how producing a 3D model of it then allows us to actually move on to the rapid prototyping stage. Okay, and obviously that's the completed product. So now we can actually start talking about what rapid prototyping actually is. So that's where it sits in the design process. I think it's important, and we're talking about rapid prototyping, but I would imagine that there will be elements of the question that will ask you about, what are the fundamental, where does it sit in the design process? So basically, that is the application of rapid prototyping. It's a fundamental step in the design process. All right. So rapid prototyping are a group of techniques used to convert a 3D CAD model into a scaled model of a physical part. So obviously, if you have a very minute sort of, medical device and you want to use a prototype to display it at a presentation, you could scale up. Or like in the case study of the baler, where you have a very large machine and you actually want to scale it down, it's possible. Or we can do one-to-one scaled models, something like this hand here, which is made to actual size, etc. Okay, and this image is just showing that we start with a CAD model. So fundamentally, rapid prototyping is the conversion of a 3D CAD model into an actual 3D object that we can hold in our hand. Okay. All right, so as we've just outlined, the initial step, the initial starting point is the production of a 3D CAD model, all right? So what we need to do then, and I have the SolidWorks logo up here because that's the example that I'm going to use here today, and you'll see this model later on and something very similar to it being produced in our rapid prototyping lab. So the first thing we need to do is convert it to an STL file. Has anyone any inclination what STL might stand for? It's relating to another term that's very commonly used for rapid prototyping, okay? And it's stereolithography, okay? So stereolithography, basically, you need to be careful because it's used to mean three different things in terms of the whole area of rapid prototyping. Sometimes it's usually used to actually talk about the whole area of rapid prototyping. It's just referred to as stereolithography, all right? It's also used to refer to as the most common file format that we use. Okay, and it's also used to refer to a specific process of rapid prototyping. All right, so you need to be careful when you're asked about stereolithography. What context is it being used in? Right, because it can actually be used in three different contexts, and you'll see me using it in all different contexts during the day, so you'll get a better understanding of this. But the first one is the file format that we use. Okay, so SolidWorks, it's a very simple process. It's not an advanced thing to be able to do. It's literally you produce your part file, you go to File, Save As, and you save it as a stereolithography file. All right. Now, as you can see in the model, what do you think it has done to the model? Too early in the morning for answers, is it? What shape do you most commonly see on the surface of the 3D model now? Someone murmured something. No? Triangles, exactly. So what it has done, it has triangulated the 3D CAD model. Okay? Now, I'll demonstrate this in the lab later on, but the degree of accuracy that the model prints then has a lot got to do with the resolution of how we produce our STL file. So if we produce more triangles, you're going to get a higher degree of accuracy. So that's a finer resolution. If we do a coarse resolution, well then, you can imagine this curved surface. If this is triangles only have straight edges, yeah? So it has converted this perfectly curved surface into a number of straight edges, yeah? So you start to lose a degree of accuracy when you convert from a 3D CAD file to a stereolithography file or an STL file. All right? But that's the initial stage. Now what we can do is, if you can imagine, there's an origin in every part file, yeah? So your 0, 0, 0 coordinate in your X, Y, and Z axis. All right? But if you can imagine, now because this has been triangulated, the CAD software can actually go to any point, yeah? So any vertex of any triangle, and calculate its X, Y, and Z coordinate. All right, so that's basically what an STL file, that's putting it very crudely, but that's basically what an STL file is used for. All right, so now when we bring the STL file to our rapid prototyping machine, the rapid prototyping machine can calculate where every single point, where every single vertex of every triangle is in terms of X, Y, and Z coordinates. All right, so that's the main reason for. Now, this is called data processing, right? So these are the initial stages. It's before we start to print anything. This is the data processing stage, and it's a key stage to the rapid prototyping process. So then there's always a software associated with the machines. Okay, they don't just use the stereolithography file format. What they do is they take the stereolithography file format and they split it up into layers. Okay, now that's fundamental, and you'll see how critically important that is as we start to look at the processes themselves, all right? But it can't split something like this up into layers. It must be something, a stereolithography, a triangulated stereolithography file. And actually, okay, so initially this acronym, STL, was used to describe the word stereolithography file, all right? And the term, I don't know if you're familiar with the term backronym, it's when an acronym is taken and then it's actually used to, so they replace these. So this was actually coined then as standard tessellation or standard triangulation language. All right, so it was obviously originally used to describe the word stereolithography, but then it was changed to actually describe what it actually does, and you'll often hear it referred to as standard triangulation language. All right, so it triangulates the model, and now it's in a format that the rapid prototyping machine can actually interpret or can actually work with. All right, so that's by no means the last step of data processing, but we will revisit data processing when we're in the lab, and I can actually show you it being carried out. Okay, so these are the processes. I think these are the main forms of processes that you're going to be examined on in this question 1 part B. So the technological process of producing a model in a fast, efficient, low-cost manner. And a lot of people will comment on rapid prototyping, and the only thing about it is that it's actually not rapid at all. All right, so you know, I'll show you a model like that hand. The build time for that hand, I think, was 3.5 days. All right, so not exactly rapid. But if you think to be able to take a 3D model and then actually hold it, to hold a 3D representation of it in your hand 3.5 days later, now that's a particularly slow process. Okay, it's a low-cost machine. It's, you know, whatever else. But this, the likes of this, which is a hat that one of our researchers designed and wore to the Galway races, it took about 24 hours to model. Okay, so it was a different process. So you can see it's more elaborate than the hand in many ways, but it took shorter amount of time. So different processes take different times. All right, and these are the most common types. Now, if you can get your head around anything today, it's a great starting point to actually be able to identify these 4 different types of rapid prototyping processes and then compare the key features of each process. Okay, so this is the second time we've seen this word now, all right, and that's what I was talking about. So stereolithography is used to describe the file format, the STL file format. It's also used to describe the first type of rapid prototyping process that we're going to look at. Okay, then we're going to look at selective laser sintering, then we're going to look at fused deposition modeling, and then we're going to look at laminated object manufacturing. Okay, and you can see their abbreviations are commonly used because they're so long-winded titles of processes. Their abbreviations are very commonly used to describe them. So we have SLA, SLS, FDM, and LOM. Okay, and they're all examples of additive manufacturing processes. Can you give me an example, or what would you think is a subtractive manufacturing process? Any ideas? So these manufacturing processes are all adding material, all right? So they don't actually cut away any material. So they keep adding layer on layer on layer on layer of material. And the advantage of that is that we have absolutely zero waste, right? So there's no waste produced when we're rapid prototyping, apart from in this paper printing process, but it's only paper that's wasted, so it's a low-cost material, okay? So in terms of adding layers of material, all right, if I was to compare that to subtractive manufacturing processes, could you think of one where we take material away?
Milling.
Exactly. So you should be able to think of a good few. Milling, turning, drilling, yeah? So all the processes that you carry out in your Leaving Cert engineering workshop, where you leave swarf on the machine, where you leave scrap material on the machine, yeah? That's a subtractive manufacturing process, because you're removing material, the process of material removal, okay? And then we also have hybrid manufacturing processes where we actually amalgamate the 2 technologies. So a part might be CNC milled first, then put into a rapid prototyping machine, and then something might be rapid prototyped on top of it, combining the subtractive and the additive manufacturing processes. All right, now I'm trying to preempt the type of things that you're going to be asked in question 1B, and I'd say, once again, that's something that's likely to come up. Could you form a comparison between additive and subtractive processes, or describe why rapid prototyping is an additive manufacturing process, etc. All right, so that's why it adds material on. It starts with the bottom layer and it builds up layer by layer by layer, and you'll see that happening in all of these processes. Okay, so the first one that we're going to look at in more detail, and I'm going to stop talking and let you look at a video for a few minutes, okay, is the whole area of stereolithography. Once again, you can see there's a CAD model involved, there's some sort of a rapid prototyping machine involved, and you end up with a concrete 3D model that you can actually hold in your hand afterwards. So let me...
Stereolithography is a rapid prototyping process used to create parts from 3D CAD data in a matter of hours. SLA is a highly accurate additive manufacturing process and may also be referred to as rapid prototyping or 3D printing. Models created with this technology are typically used as concept models for form and fit studies or as master patterns for molding techniques. The SLA process begins when CAD data is sliced into thin cross-sections or layers, typically about 0.006 of an inch thick. This data is then transferred to an SLA additive manufacturing system containing a vat of UV curable photopolymer. The machine begins to build the part one layer at a time. Each layer is constructed from an ultraviolet laser that is directed by X and Y scanning mirrors. As the laser traces the cross-section on the surface of the resin, the liquid material is hardened on contact. Once a layer is complete, the build platform is indexed down to make room for the next layer. A recoater blade moves across the surface, ensuring a thin coat of fresh liquid resin is evenly spread over the object. The laser continues to trace and form each layer atop the previous layer, building from the bottom up. The completed part is then carefully removed from the liquid and separated from the platform. A chemical bath removes excess resin, and the part is cured in an ultraviolet oven. Any support structures are removed at this time. With numerous hand sanding and professional paint options available through service providers such as Solid Concepts, stereolithography has become an excellent economic choice for rapid appearance models. A wide variety of industries have embraced SLA, including medical, automotive, entertainment, aerospace, and consumer products.
Okay. So the video gives us a real nice insight into how the actual stereolithography process works. So that's the SLA process. Now, the key elements of that process are that, okay, it starts with the medium that it starts to produce the prototype from. So that's this model here. That would have been produced using the SLA process. This plastic part of this, you couldn't call it a hat, headpiece, whatever it is, okay? So that was produced using that process. And what happens is, a vat, okay, so it's called a vat, is produced with, or is filled with, photosensitive polymer fluid. Okay, so the polymer is in a fluid format and it's photosensitive, so it's sensitive to an ultraviolet light wave. Okay, so when an ultraviolet light wave hits this polymer fluid, it solidifies. Alright, and that's the whole SLA process. Okay, the fact that a UV laser is able to solidify this fluid polymer. Alright, so how does it control the layer then? Did you see from the video how it printed layer by layer? Yeah? What happened? Okay, yeah, exactly. So there was a slider coming across. So what happens is it has a platform, all right? The platform moves in the z-axis, all right? And then the laser moves in the x and y-axis using the deflection of two mirrors. Yeah? Okay, so what happens is it produces the bottom layer of the object, okay? And then what happens is the platform moves down the thickness of one layer. Okay, so you can imagine that machine has taken, first of all, it takes the object and splits it up into layers. So the machine does that using its own specific software. So it's sliced up into layers, all right? And then the laser technology starts to shine down and actually print the initial layer, okay? So you can see that's the production. So this is the laser beam coming down, and it selectively only goes across that cross section. Okay, so imagine dividing this fan or this, whatever it is, some sort of turbine blade up into layers, and it prints each individual cross section. Okay, so I was asking our researchers typically what sort of thickness do they print the layers, and they said that the default on the SLA machine that we have here is 0.1 of a mil. Okay, now that's the default resolution. Okay, so you're going to have to print 10 layers to produce 1 mil of thickness. All right, and they said that's as thick as they'd ever go. If they were ever going to do anything, they'd refine the layer thickness. So they'd reduce the layer thickness so that you get a finer resolution of a prototype produced. Okay? So, and that's all controlled by the movement of the platform. So the platform moves down 0.1 of a mil. I don't know if you saw the blade scraping across. So the blade scrapes across just to make sure there's a nice even layer of new polymer fluid sitting on top of the model. Okay, no bubbles, for instance, or no impurities sitting on top of it. Scrapes it off, make sure that there's a clean layer sitting on top, and then the laser starts to solidify the next layer. Okay, so that's the basic fundamental concepts of that, and you can see it builds it up layer by layer by layer, and then eventually you're left with your end product. Okay, so you can see this is the end product. But obviously, if you have a product that has an overhanging feature, underneath that you have to build a support structure. Okay, so it's made out of the same material, but it's made in a lattice format that's very easy to crack away afterwards. Okay, now what I liked about that particular video that I showed you is that they actually did include the whole area of post-processing. Right? So now I've talked to you about data processing, taking our CAD model, converting it to an STL file, bringing that STL file to the machine and splitting it up into layers. That's all part of the data processing. And then you go about printing it, so the rapid prototyping process is carried out. Once it comes out of the machine, it's often the part of rapid prototyping that the rapid prototyping companies don't talk about because it's the most time intensive, and it's post-processing. All right, so almost every rapid prototyped object requires some sort of post-processing. In this case, it'd be the breaking off of all of this, all right? And you can imagine where this attached to the bottom surface, you're going to be left with a rough surface finish. So there'll be sanding, maybe some chemical processing done to it to smooth it out, etc. And then it might have to be primed, spray painted, etc. to get it to the requirements of the prototype. Okay, and that's known as post-processing. Okay, so that's SLA, and that's kind of a schematic that you might want to try and convert into a 2D diagram that you're able to draw. So a laser hitting a mirror, coming down into a vat, all right? And just interestingly, the machine that we have here in the college, the bed on the machine is 300 by 300, okay? So a steel ruler by a steel ruler, all right? And it's a little bit deeper, I'm not sure of the depth, but it's maybe about 500 mil deep, okay? And to fill it with the photosensitive polymer fluid that we currently are using costs 40,000 euros. Okay, so not a cheap process. All right, so even though rapid prototyping is considered to be a low-cost process, to get a part produced is going to cost a company a few thousand euros. All right, now obviously, to produce one part doesn't use up 40,000 euros. The only thing that's used up is the material that it actually works on. It's an additive manufacturing process, so there is no waste. Apart from, sorry, the image is gone, but apart from the support structure that needs to be broken away. So that's the only waste in this additive manufacturing process. Is that okay? I really want you to understand that process because the next one is very closely based upon it. There's only one fundamental change. All right, so now we're moving on to selective laser sintering. And this is quite an interesting video here because it's Adidas are actually using this technology to develop a sole for a runner that they're trying to develop. All right, but the advantages that you can imagine for Adidas are that they can maybe have you go to your local running shop, all right, and the running shop is able to scan the sole of your foot, right, and send that off. Yeah, Adidas can convert it to an STL file, and now they can print the sole of your runner to exactly suit your foot. Okay, so you can imagine where that technology would bring it. This is so Solid Concepts, which is the company that I took these videos off. This is a competition that they ran to get teenagers to design a skateboard using 3D CAD modeling software, and then the winner they decided to print it in SLS. So let's have a look at the Adidas video. It's not based on the process, but it does show the critical difference between SLA and SLS. Okay, so as such, the process wasn't exactly wasn't highlighted. But from that video, what do you think the main difference between SLA and SLS is? No, believe it or not, there's still no waste.
Made inside the powder.
Sorry?
Made inside
In what? Powder, exactly. All right. So the difference is that instead of using a polymer fluid, now they're using a polymer resin. So a very fine polymer resin. So you can imagine that dust is just very small particles of polymer, okay, of plastic. It still uses laser technology, so it's a very similar machine setup. There's still a laser operating on layers, very fine layers of powder. Okay? And if I show you this diagram, it explains the process in a little bit more detail. Compare the post-processing of the Adidas insole. Did you see him post-processing the insole? What did he do? He literally shook it, tapped it off his hand. The post-processing is shake the powder off. Okay? Maybe get compressed air and blow away excess powder. All right? You're correct in that there's a large mass of powder that it comes out of, but it's not wasted, all right? It does have to be processed so that it's actually make sure that none of it clogs up and it is a fine powder again. So it's just put through some sort of a sieving process, but then it's completely usable again. So zero waste once again in that process, all right? So we have something very similar going on here. We have a moving platform that's moving down in the z-axis. We have a laser beam that's operating in the xy, all right? So an xy scanning mirror, so that's moving the laser in the x and y axis, okay? And then we have a powder feed supply here on the left and also on the right, just for efficiency. So you can imagine this is moving down and these are moving up. So when this moves down 0.1 of a mil, this moves up. A fresh layer of powder is brought across by this roller, so it's rolled across, okay? So the small gap that was left by this platform moving down is now filled by this roller, okay? So the powder isn't just left sitting on top, it's actually compressed onto the top of the previous layer by a roller, okay? Yeah, and obviously that roller stays over this side, the next layer is done, this moves up, the roller comes back this way then to put a fresh layer on for the next layer to be sintered. Okay, so now we're talking about selective laser sintering. Okay, selective in that the laser only goes to the area that needs to be printed. All right, laser because that's the technology that's used to actually carry out the sintering. And has anyone ever heard of sintering before? No? So sintering is it's like welding, okay? But sintering is when you take molecules and you actually solidify or liquefy the molecules so that they flow into each other and then let them cool and they solidify. So you can imagine why it's used to describe this process. Because the powder that's left sitting on top is melted by the laser, yeah? They obviously become liquid, flow into each other, solidify, and that's that layer of that cross-section produced. Okay? Is that clear? All right, so the main difference here being the medium, all right? One being, so SLA, stereolithography, using a polymer fluid. SLS, which is selective laser sintering, using a polymer resin or a polymer powder. Okay, the next one is fused deposition modeling, or FDM, okay? Now, this is slightly different technology. No laser involved, and this is actually quite similar to if you imagine your inkjet printer at home. Okay, so you have an inkjet printer at home, and all it has is a cartridge of ink, and it uses a nozzle to put that ink on a piece of paper. Okay, so this technology uses a similar type of technology, but instead of ink coming out of the nozzle, it's an actual polymer coming out of the nozzle. Okay, so it prints a layer of polymer, the platform moves down, it prints the next layer of polymer. Alright, so instead of me talking, I'll show you a video once again. So this is MasterBot, this is the actual machine that we have out in our Applied Polymer Technology lab.
Fused deposition modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform.
Okay, so this has been the fundamental difference now. Now we don't have any polymer.
Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part.
And it's being fed up through the machine, it comes down through heaters, right? And by the time it comes
Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts including hand sanding, assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and Ultem, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical.
Okay, so once again, that's if you YouTube that Solid Concepts company, they have excellent videos of all of these processes that you can look back over again. But once again, it really nicely shows how that process is carried out. Yeah, the difference there was there's two different materials used. One used for the actual product, and another used for the support structure. Yeah, so there's two spools of different polymers being brought in. One would be a lower density, so the support structure would be a lower density, more brittle material, so it's easier to break it away when you're finished. So it makes post-processing a little bit easier. Okay, but usually there is quite a bit of post-processing with the FDM process. It mentioned things like excellent weight to strength ratio. Okay, so very light products can be actually quite strong. And also what's interesting there is sometimes when we think of a prototype, we think of the Kellogg's cornflakes box or the piece of foam after being carved up, and it's not actually functional. Whereas all of these rapid prototyped parts are actually completely functional. Okay, so they can be brought to consumers and actually tested. Yeah, they're not just flimsy models. They are actually functional parts. They're made out of, as he mentioned there, thermoplastics. Okay, so they are actual polymer products that can be tested, etc. And also the other thing about them is the complexity. So I meant to actually mention that about the Adidas, the sole of the Adidas runner. Like you could see the cross section of that runner was a very complex kind of lattice. It was a kind of very complex structure, and you could see the product testing then was allowing a hell of a lot of flexibility, etc., for quite a small amount of material. Yeah. And also here in this image you can see the complexity of some of the models that are almost impossible to do using other manufacturing processes. All right, and you'll see other examples that I'll show you including some of these, like that sphere. You know, it's made up of a number of hexagons, etc. But you know, incredibly detailed geometry that isn't possible to manufacture using any other manufacturing processes. This is another chess piece, but okay, it looks ordinary enough, and you can imagine it's easy enough to manufacture using maybe an injection molding process, etc. But when you look inside it, there's actually the stairs is in there, running through it. So you'll get to see that later on in more detail, etc. All right. So that's FDM, right? It's a little bit more familiar to us because it uses similar printer technology to like what we're used to, just printing in the X and Y axis, depositing a layer of polymer, moving down the thickness of a layer, and then depositing another layer of polymer, all right? And then this is laminated object manufacturing, and I'm going to talk very little about this here because you're actually going to see this in operation in our rapid prototyping lab later on, okay? So it uses So in this diagram, it's using laser technology to actually cut a layer. So same thing again. We have a moving platform, moving down in the Z-axis, but we have a sheet. So what's laminated? What does laminated mean? If we're talking about laminated timber, what are we talking about? Yeah, so sometimes laminated timber is plastic coated, but what are we actually talking about when we talk about laminates?
Layers.
Exactly. Layer upon layer. You're probably sitting on some, eh? Yes. If you look at the cross section of the desk in front of you, you can see all the different layers of timber in front of you, yeah? So they're laminates, all right? So they're all sheets of timber all just glued together. And this is the same concept here. So basically it takes a sheet of plastic, or in this case, paper. So this hand was modeling this. And that's, I don't know how many sheets of paper in a ream. It's about a ream and a half of paper thick. Okay, so you're probably talking about 500, 600 sheets of paper to produce this model, right? And it's just sheet of paper brought in, cut that cross section, bring in another sheet of paper, cut that cross section, and they're all adhesively joined together, so adhesive bonding. So they're glued together basically, all right? So you can see here, this is just a spool of the material being brought in, the cross section is cut, the next one, and this is the heated roller, so they're heat activated polymers, all right? So you put the heat activated adhesives, right? So you put the adhesive on that layer, the heater rolls across, activates the adhesive and sticks the layers together. All right? We're going to talk about that in a lot more detail. And then these are two more high-end processes that I'm going to talk to you a little bit more about in the rapid prototyping workshop. Any questions? So I've covered a lot of stuff there theoretically, so you will have an opportunity in smaller groups to have a chat about this and explore the different areas, etc. An area I'm not going to go into a lot of detail here in the lecture is the applications of rapid prototyping, but you can see that almost every industry now is affected or is employing the applications of rapid prototyping, including the automotive. That's a completely rapid prototyped car. If you can imagine an exploded view of a car, you're talking about hundreds of thousands of different parts. Right, and that's excluding the engine, talking about just the body of the car, etc. I think this car was built in 47 parts, right? So the rapid prototyping cuts out a hell of a lot of the assembly of the car, all right? So all the smaller parts, it's actually possible to rapid prototype them, etc. The medical industry is one that I find most fascinating in terms of uses of rapid prototyping. You can see this is a fairly serious skull injury, okay? But what they were able to do was carry out an MRI of the patient, all right, actually calculate what sort of a fracture was there, what sort of a void was there after the skull injury, and then rapid prototype a medical grade polymer that could actually be put in there to fill the void so that that patient could recover completely. Okay, so some amazing stuff going on in the world of medicine. Even in sports, I don't know if you're golfers, but if you're aware of the new rule in golf, all of those guys that use that long putter that they anchor on their chest, from this year on they can't use it anymore. Okay, so a company jumped on the bandwagon there and actually created a training tool to actually train golfers to actually hold the putter in the correct grip. All right, and it's rapid prototyped as well. Because of the complex geometry, very, very difficult to produce that, any other way. And then obviously the hairpiece, which is an example of what I have here in front of me. So even the fashion industry is starting to use it, etc. And you even saw like the footwear industry and the Adidas sole, etc. And all of those companies, if you look up, rapid prototyping of sportswear, Nike, Adidas, all those guys are all jumping on this because they see the visionaries in all of those companies see this as the next thing. And I suppose the visionaries in terms of rapid prototyping see that maybe we won't all have one sitting in our study at home, but that like when we used to take photographs on a digital camera and go to the pharmacy to print our photographs, now what we'll do is we'll shop online, we'll buy a 3D model, and we'll maybe go to the pharmacy and print out a 3D model of whatever that product is that we want, etc. Okay, the NASA are using it now where they think sending spare parts up to the space station is a waste of time if they just transported one rapid prototyping machine up to the space station. Then they could send the models up and the engineers could print out the spare parts up there rather than transporting parts to space, etc. So you can see the possibilities of the technology is endless really. But we will discuss, and I'll give you more of an opportunity to look at the actual applications of rapid prototyping in the workshop. You'll get to handle all of these existing examples as well. Any questions? No? Didn't think so. Crystal clear. Question 1B sorted. Okay, good stuff.